So hi, my name is Michael Bailey. I'm with the University of Michigan. I'm up here with Timothy Battles from AT&T, and today we're talking a little bit about the Internet Motion Sensor project. So I think you're all going to be terribly surprised to understand that there are a bunch of really nasty things on the internet today, like denial of service and worms. I think you'll probably be equally surprised that somebody somewhere thought that that was a good monitoring project. How does IMS do its monitoring? As the saying goes, all the good ideas in computer science were invented before 1970. That's probably not true for this one, but pretty darn close. We do what you guys have been doing for a while. That is, we use the routing infrastructure to offload packets from the network and analyze them. Of course, when you have an OC192 backbone, the problem becomes one of trying to figure out what it is that you want to offload to analyze. Fortunately, there's a couple situations in which we have some pretty clear indicators that something's going wrong, and there's some clear indicators of what to pull off. This includes attacked customer traffic in the case of DNS, traffic outbound to space that's not allocated, and stuff inbound to parts of your network that actually don't have hosts in them. We like to look at the inbound traffic to unused address space. Part of the reason we like to do that is that the traffic itself is pre-filtered. Because there's no host in that address space, we shouldn't be seeing traffic, and the traffic we do see is because somebody is scanning, there's worm propagation, there's misconfigurations, there's backscatter. So if this is starting to sound familiar, it should. There's been a lot of really good work by folks in this room, in this area, including the work by the folks at CADA as well as Team Cumry. So why should you not skip out and go to an early lunch? Well, I think there's a couple interesting things about this particular project, and they derive directly from the design goals of the system. The Internet Motion Sensor project was designed to do 4 things based off of some of our experience doing early monitoring of this type. In particular, what we wanted to do was be able to differentiate services. Oftentimes, new exploits come up for ports which already carry a lot of traffic in this space. Of course, not all the new exploits and vulnerabilities happen on ports that we already know, so we want to be able to capture those as well. In addition to which, we want to have broad representative coverage of whatever threat it is that we do see. And finally, we want the system to be available if it's going to provide any utility during these times of new worms or threats. So why do we care about differentiating services? As I pointed out earlier, oftentimes we see new threats on ports that already have traffic. In this particular case, we see a graph of TCP 445 traffic as represented over a 7-day period observed at one of our sensors. This graph was taken around the time of the SASR outbreaks. And as you can tell, before SASR came out, there was a great deal of 445 traffic on this network. Well, since I told you that SASR came out during this week, you can probably guess where it came out. If you hadn't known that piece of information, it might have been harder to do. It's not until you spend some time looking at what the infections are trying to do, as we do in the upper right-hand corner, that you can actually see that there's a signal within that noise. Why is it important for us to capture new services? For those of you who monitor dark IP space regularly, you know there's a handful of ports that are always in the top 10 list. You also probably know that the rest of the top 10 list varies pretty widely based on what network you're in, what time of day it is, what the fashion of the day is. In this particular case, we're looking at a graph of the big changes in ports from 5 months ago to today. One of the things I think that was interesting to look at is these 2 ports, 2745 and 3127, which were representative of backdoors. 5 months ago, these things did not exist, or 5 months ago, as of this graph, they didn't exist. And all of a sudden, they shot out of nowhere. These, of course, are people scanning for the back doors, thinking about these worms. So if we didn't capture information on these ports, if we didn't have a monitoring infrastructure that was capable of storing things across them, we wouldn't be able to gather this information. Obviously, broad coverage is in great part about getting as many sensors as you can. The more space that you have, the broader the coverage, the earlier the time to detection, the better the representation. But it turns out also that different sensors see different things. In this particular slide, we see the average packet rate over a week as seen by 10 different sensors in the sensor network. The first thing you'll notice, obviously, is the large difference in the magnitude of the traffic. And this traffic, in fact, is not the result of local preference by people in the same /8. In this particular case, we've removed all those source IP addresses that are in the same local /8. You still see these large differences. Finally, we wanted whatever infrastructure we built to be available. It doesn't do any good to be able to react and respond to a threat if the box is down during that threat. This is actually a little bit more complicated problem than actually just building good software. In this particular case, you see a view of the Witty worm as observed by 3 of our sensors. we thought we had some pretty good diversity in these sensors. They're all in 3 different /16s. They're all in 3 different organizational units. They're in 2 different /8s. But it turns out they share the same upstream provider. And around the time of WIDI, a couple hours after it started, the upstream provider was trying to debug a problem with one of their customer routers and inadvertently placed an ACL across their entire border to block WIDI traffic. So how do we achieve these sets of goals? The IMS architecture contains a distributed set of sensors. Those sensors, we make an attempt to make sure that they're topologically and address space diverse. We differentiate services by replying to TCP SYNs with TCP SYNACs to elicit the first payload of a TCP connection. We use payload reconstruction and MD5 checksums to build signatures of those payloads, and we try to respond across all services. So what does the current distributed IMS deployment look like? Right now we monitor 28 blocks at 18 different networks, including a variety of academic, service provider, and large businesses. We have a variety of spaces from very wide as a /8 to a lot of small spaces like /24s. As I pointed out before, key to what we wanted to do is to differentiate services. UDP and ICMP are easy. These type of attacks contain the data payloads that we want to look at without eliciting or doing anything fancy. However, TCP is a problem because we don't actually see what the application level exploit is until we actually initiate the 3-way handshake. So our solution to this is to build a lightweight active responder to get the first data packet. The solution is pretty simple. We get a SYN, we SYNAC it, and that's generally enough to get enough of the payload to differentiate the threats. So how does this look? Let's look at this in the context of the Blaster worm. For those of you who don't remember, Blaster was TCP port 135, a buffer overflow against an RPC service from Microsoft. At the top, this particular graph is showing an infected host and a vulnerable host. So this is what you would see if you were TCP dumping right in front of a box that was about to get infected with Blaster. The top part of it is the standard 3-way handshake. You then see the application level RPC bind and then the actual RPC request, which is the buffer overflow. There's the session teardown. And for those of you who remember this particular worm, the payload itself, in terms of what the worm was supposed to do, as well as the commands, were executed over port 444. Once that session was torn down, the infected host would attempt to contact the exploited host on 444, send it the payload in the A variant of Blaster, it's a denial of service attack payload, and then tell it to actually execute it and hit. So what does this look like in the context of IMS? Well, again, as we mentioned earlier, what we're trying to do is elicit enough of the payload to differentiate various threats. In the case of Blaster, you can see the IMS or black hole sensor replying with the SYNAC. That's enough information for us to elicit the RPC bind as well as the RPC request. You'll notice that the session teardown stuff is not there because we don't store state. We just reply with the SYNAC. We're not trying to do full session reconstruction, and that's part of the reason we get the scale. It's also the case that with respect to Blaster, there's no real check to see whether or not the exploit actually took effect. So immediately following its buffer overflow packet being sent, it goes ahead and tries to connect on 444. If you respond on that port, you also are able to differentiate and get a hold of the payloads as well as the commands. So one of the problems with this particular approach is that if you start eliciting more payloads, you have more payloads to store. And we saw a drastic increase in the amount of stuff that we were storing on disk. One of the first solutions we tried to this was, hey, let's just store new stuff. And the way we did that was we took an MD5 hash of the payload and only stored payloads which have a unique hash. One of the cool things that happened as a result of looking at that was we pretty much found that if you look at the first application payload across all these different exploits, worms, and things you see, that most of them have been seen before. And in fact, a very, very large percentage, almost 95%. In this particular graph, you're looking at the cache hit rate as observed by 3 sensors over a period of 5 months. So, why is this thing useful and why do we care? Hopefully, folks here will remember the Sasser and Dabber worms of earlier in May this year. Sasser was an LSASS exploited an LSASS vulnerability. It scanned for vulnerable hosts on TCP 445. Once the boxes were exploited, they installed a backdoor on 5554. There are a bunch of different variants of Sasser, including Sasser E, which most notably changed the backdoor port to 1023. Dabber was an interesting worm in that it actually exploited a vulnerability in the backdoor of another worm. So what Dabber did was scan on 5554, looking for backdoors created by Sasser, and exploited a vulnerability in the FTP server of Sasser, and then itself installed a 9898 backdoor. So why do we care about those particular threats? Recently, folks have been seeing a lot of scanning activity towards these 3 ports, and most of the scanning activity looks like this. Large double spikes. The same kind of graph is this, what you would see across all these ports, 1023, 5554, and 9898. And very interestingly enough, almost all the hosts, and I don't mean just like the normal distribution, I mean like 98 or 99% of the hosts are from Korea and from China. So, as you noticed in the previous slides, the spikes were not overlapping as seen by 2 different sensors. If we look at 4 different sensors over time, we can see that this is in fact actually a top-to-bottom scan of the internet. We do a couple quick calculations on time and amount of IPs scanned. We see that they are in fact doing a top-to-bottom scan, and they are doing it about 6/8 an hour, which is just about enough to get through the non-reserved space in a day. One of the interesting things about this particular attack is it seems to be done from a very large pool of bots. This particular graph shows the cumulative unique IP addresses over time. I've highlighted 3 different regions that correspond to the 3 different spikes that we saw over that 3-day period. There's a couple things to note here that are very interesting. There's only a small number of hosts that are involved each time as observed by each sensor, but the size of the humps is similar each time. This is a cumulative unique IP address graph. So if these IP addresses were being used again for the next day's scan, we'd expect the bumps to be smaller and smaller. They're in fact not. And it's also interesting to note, although it's not relevant to this particular scan, that these scanners are actually being dwarfed by the amount of background noise and other scanning activity that happens on those ports, even though the spikes themselves are quite large. So we saw that there wasn't a lot of reuse between IP addresses as seen at an individual sensor over time. Is there a lot of reuse between sensors on the sensor network? That is, are those IP addresses scanning multiple blocks? That turns out not to be the case as well. What we're looking at here is the overlap or intersection between 2 different sensors and the number of unique IP addresses that appear in one scanning for a specific port and appear in another for a scanning port. The region of this graph that's very interesting is the lower left-hand corner, in which we see the overlap between the /18 and the /17 in terms of IP addresses involved in scanning specific ports. You'll see that there is no overlap among the 400 IP addresses that were scanning 1023, and only a very small handful of overlap in the other IP addresses. The takeaway from the last 2 graphs, this one and the one before it, is that the person who's doing the scanning already has a very, very large pool of disposable IP addresses that they do the scanning with, and they don't reuse it across scans and blocks and across days. So what were they doing? TCP 9898, they were just SYNing to see whether or not there was any activity or a service available on that port. There were 2 unique signatures for 554 and 1023. Here are the MD5 checksums and the hex dumps representations of those 2 signatures. But user X and D are just part of the backdoor protocol for Sasser, and it's actually an application message trying to see whether or not the backdoor responds. So hopefully you've seen a little bit of why IMS is unique and what some of the utility of the infrastructure is. If you're interested in getting involved, this is a publicly funded research project. If you've got space that you want to donate to the project and become involved with, we do have some equipment that we can send out to you. We're also building a software-only version of this, the software, so you could download it for your own private use or participation in IMS if you'd like. What you get when you participate with IMS is very much the you show me yours, I'll show you mine kind of attitude. You get aggregate views across all the other participants, and you get detailed views of all the information that are handed over to your blocks. So I want to hand it over to Tim to talk a little bit about why this is useful in an operator context.
So I get the real easy part of this presentation because mine's really extremely short. So what's the importance? All right, so what's the importance? I mean, most importantly, we have early detection for the worms and viruses. Second, we can provide the source addresses that are trying to hit these dark address spaces. We can provide these lists to our abuse groups for cleanup. Pretty much anything that's hitting dark address space is going to be some type of malicious variant or scanning, or it's not supposed to be there. It provides baselines on footprint measurements. One of the things we do is there's a lot of complaints about the white noise that's going around on the internet. So we have customers that have a /16 or have a /8 or some rather large blocks. And we can kind of baseline what we receive on our dark address space. And we can go to the customer and we can say, well, 100% of your bandwidth out of that, 5% of this is being allocated to just internet noise. Let's do a footprint reduction so that you can recoup some of that cost. So why do we need payload? One, it enables the detection of new variants. If we're not looking at the payload, if we're not looking at the signatures, if you're just relying on something hitting port 80 or something hitting port 9898, how are you ever going to know if there's a new variant? The typical dark address space isn't going to pick up a whole lot of trend unless you can pick up on some type of payload, and we can be bombarded by an entirely new variant and not even know it. Can be used to create IDS signatures. If a new variant does get released, it's a really quick method that we can take that signature and we can rapidly deploy to our IDS sensors as well as our firewalls and block it. Enables variant tracking independent of associated port. Once again, it kind of goes into what's the purpose of just looking at a port? If you're not looking at something that's a new variant that's going towards the port and using that payload, it doesn't make any sense. Source address distributions. So you can set a priority. Because we're collecting source AS distributions, we can say, where's the threat at? Are most of these sources, are they coming from Asia Pac? Are they coming from North America? Are they coming from South America? Are they coming from our European ASs? It allows us to prioritize in the case of an emergency. Something breaks out, a new virus, a new variant breaks out. We know where to start placing our access list. We know where to start our mitigation, and we know how to finish our mitigation. It's real time. So really, do we really need to answer this question? If our data is a day old, if our data is 12 hours old, it does us no good, except to say, why did this happen? But if we're going to prevent outages from an operational standpoint, we need to have real-time data. And so bringing it all together, this is kind of more of an eye chart. I don't know if you guys can see it entirely, but essentially you can operationalize this. If you're monitoring something from IMS, you can determine whether or not you have a new variant. If no, you still have the tracking capability of the variant, of the old variant. See if it's increasing, see what source ASs it's coming from. Send the source lists up to the abuse desk for cleanup. If it is a new variant, we can go into mitigation. And from that mitigation, we can determine what's the severity of it. Is this localized just to my ISP, or is this global? Is this hitting all these other blocks that the IMS has coverage for? If it's local, regardless of if it's global, you can notify the proper people. We can do firewall updates. We can do IDS updates. Update perimeter filters. Activate tar pits based on that. Vendor updates, contact a vendor because we have the payload. We can immediately send that off to the vendor, see if they already have a known patch and patch it. That's it. Thank you.
Thank you.
You guys can't sit down because there's a question. So, yeah, if there are any questions, please stand up quickly so that I can get a good count, because I'm hungry and I want to leave for lunch. So.
Have I been counted yet?
No, you are invisible. You're an any cast instance of the bill protocol. So you want
So
to go
I'm
to
not
lunch.
even a one? You guys can take this sitting down, though. Question about the IMS project. Is there any reason why we would need to dedicate a whole subnet to it, or is just seeing all of the, if instead of black holing a cover route for our announced prefixes, if we just send them all to one place, so anything we don't have a more specific for, we send past your box, is that good enough?
Yeah.
Yeah? Okay.
Yeah.